Hey, what's going on, guys? Games here. So I've been playing around with KIM-1 software on various emulators, but the problem is that neither of those I've encountered so far is accurate enough. So that's the reason why finally I decided to start writing my own emulator. And it's gonna be a sort of a video documenting series on how I proceed with this sort of a thing. I'm completely new to writing emulators. Well, I had a bit of an experience like writing an emulator for an imaginary CPU of my own design, but that was just that wasn't really that serious. Okay, and this time I'm not starting from scratch, so I'm not writing a 6502 processor emulator. I'm using the existing one, which is hopefully it is cycle accurate as the README file in the GitHub repo mentions. But anyway, if not this, then I can pick another one. Doesn't matter really that much. So on the other hand, I've prepared a sort of a library to display the 7-segment LEDs. It just draws the canvas, and it's not connected to anything. It's just a bare the visual proof of concept that it kind of is capable of drawing the 7-segment LEDs and lighting them up based on some specific codes, right? That would be set up by the processor. And here, here's my CPU running the KIM-1 ROM. We'll get back here just right in a moment. So I don't yet have the keypad. I don't yet have the I/O emulation. I don't have anything at the moment. And I just wanted to tell you where in particular am I getting started, because, you know, like, no matter how long I've been trying to find some decent information on creating emulators, I don't know, all the resources I came up with so far, they didn't really answer like those questions that I had. So probably just assume that you already know that. So hopefully maybe these kind of videos and the description, the showcasing of the approach I'm following would potentially be helpful to anyone trying to kickstart with writing an emulator on his own. And again, like here, by saying writing the emulator, I'm not focused on creating the parts of the emulator, like the CPU, like, and the rest of things, but I really want to emphasize on bringing things together, and actually we're fighting for the accuracy of the emulation. That's the major goal. That's the major reason why am I doing this, basically. So yeah, let's quickly walk through what I have here so far. So here is the project structure. So index.html is the file. This is the index.html I'm running here. So it doesn't do much really. It just uploads all. Let me just probably show you that. So it just uploads all the JavaScript files. So the library to draw the 7-segment LEDs relies on P5 library. That's just a fancy wrapper around the canvas elements. You can easily draw the canvas like using the setup and draw functions, so without being bothered by manually setting up the frame rate and things like that. It's quite handy. So here are the codes to actually draw this this proof of concept display, but it's not doing anything again. Like, it's just, I just want to make sure that I can't use the first one I picked out there. So it's just, I don't know, maybe I will replace it. Doesn't matter at the moment, really. It doesn't do anything at the moment. So the main code that we're interested in are these two libraries. So we have the 6502 dev.js. So this is the 6502 CPU emulator by, oh my god, I forgot the guy's name. I'll give you the links in the description below the videos with all the credits. I just don't remember what was the guy's name at the moment. And this is the file where I'm already writing something on my own, and it's supposed to be the file for like the emulator, the main, like bundling all together, right? And the segment.js and segment.display.js are related respectively to the display. So it's not like just not connected to the CPU at the moment, really. All right, so now I know probably there are many various approaches on where to get started basically. And I need to say that in order to avoid being kind of horrified by the amount of work that is needed to be done, and in order to have a sort of a guideline before actually before actually taking a decision to write these kind of emulator, I've been watching two series by Ben Eater, so the 8-bit breadboard computer and another 6502 based computer. And well, if the 8-bit breadboard computer helps like generally to understand how the data is being exchanged in the 8-bit systems between the registers via the 8-bit bus, and how the clock is kind of synchronizing all the stuff, what is the cycle, why some operations take more cycles, others less, etc. So all this kind of hardware circuit level basics actually bring some light. So you don't need to emulate the things on the circuit level, but understanding, at least seeing how someone explains how things are working on the circuit level is really helpful. For me personally, this was absolutely essential then to get away from the dead end, because otherwise I was just completely stuck forever, and that's pretty much all about it. And another tutorial series is how Ben was building the 6502 based CPU, and that was the most essential. So when he was connecting the ROM chips, programming the ROM chips, and connecting the pins between the processor and the ROM, and then the I/O, and that was really like a feeling like you can touch things, and that was really helpful in order to figure out and understand like where is the entry point, so where to start basically. Okay, so that just allowed me to get rid of some fear of doing this, and it just brings some light to just where to get started. Okay, but as far as I don't have a real KIM-1 and I can't actually play around with it, I can't like turn it on and see what happens, like yeah, so I can't do that. And also I don't have a decent emulator that would be 100% accurate in emulating how the ROM works, for instance. So I decided to pick up a different approach. So two kind of milestones I rely on is the logic of how the 6502 CPU's interrupt request works, and the KIM-1 ROM itself. So let's start from the KIM-1 ROM basically. And I don't know, so why my camera is so laggy? I'm sorry guys, probably because I just probably because this app is running, maybe. Okay, sorry. So okay, so it's, yeah, it should be better now. I don't know, for some reason it was incredibly laggy. Okay, so hopefully now it's fine. So there are two ROMs. There were two ROMs on the original KIM-1. For some reason they are named ROM 003 and ROM 002, and I took the ROMs themselves with these are supposed to be the original ROMs, and quite handy thing that they have the commentaries in 6502 assembly, and even with the commentaries to the assembly itself, which is incredibly helpful. And I took this from the KIM-1 project by Oscar Vermeulen. This is really helpful, so it should be like the 100% original KIM-1 ROM. So there are two files. So this one called ROM 003 is responsible is literally a KIM monitor. Okay, so it's kind of like an operating system for KIM-1. So when you just turn the KIM on, and you can just type address and switch to the data mode and type the value there. So in order to make this kind of possible, this code in this ROM 003 is needed, right? And in another ROM, for some reason it's called ROM 002, and it's the ROM to oh my god, to deal with the cassette tapes, right? And I'm still including this because for some programs, not having this ROM might be crucial, so they're just not going to be working, like KIM-1, for instance. So yeah, these are two of the most essential like memory spaces, let's say. Well, from the processor perspective, the entire memory space is like from 0000 to FFFF, like 64 bytes, sorry, 64 kilobytes, right? But if I went that way, so I need to waste like the most of lots of memory would be just wasted, because all we need is around 1K for ROM 003, somewhat a similar amount for a second ROM, for ROM 002, or okay, it doesn't matter how they call it. So here is the trick. The 6502 processor, in order to, like when you reset the computer, in order to get the program counter of the 6502 processor, an idea of where to get of how to get initialized. So in order to initialize the program counter and actually start doing something, start executing some instructions, and most likely these are going to be the instructions within the ROM, because the ROM is kind of looping forever, and that's kind of the operating system. So in order to give a program counter an idea where to initialize its address, it's given at address FFFC. And if we have a look, at the routine to reset the processor, you see like a register is getting set to 0x0. So this I don't know why this if this is a stack, I'm not sure. It's not my code, so I can't say for sure if the stack is set to 0. Okay, we can come back to this later. Yeah, it just commands somewhere. Okay, but anyway, the most interesting thing here is actually this one. So the program counter. Why, you might be wondering, why do we need this left bit shift left? Well, that's because of the little endian byte order in the 6502 processor architecture. So if you want to pick up the address, so first you store the least significant byte and then the most significant byte. So this line actually reads the address from there, and eventually, and then here is the first nibble. I'm sorry, here is the first byte, and here is the second byte, and eventually, after this operation, so it happens when you reset the CPU, the program counter starts pointing to the certain address in the ROM, and this is the most essential entry point that I want to emphasize. So here is the main. So you just imagine that this web page has just started. I'm not starting just to avoid the lags with the camera. So yeah, if I just don't print anything to console, it would be much better. But okay, so once we start, right? Well, actually, we started like a bit earlier. Well, anyway, so the first, so here we have the infinite loop, and what this loop does, it just asynchronously calls itself forever. And during the loop, what we essentially do is we are executing next instruction the program counter is pointing to in the loop forever. Okay, but before that, in order to give the program counter a proper entry point, so where to point, so what would be the first byte to execute, we need to reset the CPU, hence the CPU reset, and somewhere, yeah, actually, it would be better. Yeah, it's better to say code starts kind of here. So here we're creating the CPU object. I'm also defining two custom kind of API functions. I don't know how to call them properly. So these are the user-defined functions to read the memory and to read from the memory and write to the memory. We'll talk about these lines a little bit later, and they are really they're absolutely essential as well. But the most interesting thing, that once we've executed this reset, then the CPU actually gets the address from FFFC and FFFD. And in order to get an idea what kind of address does it get set to, we can go to this. So here I've separated the interrupt requests separated in order to avoid wasting the memory. So actually, if this was a real chip, a real ROM chip, then at 1FF7 there would be the last these, like, well, actually this not doing much, but actually here is the end of the ROM code, okay, and then from this address and up to this address, it just should be filled with FFs. But I don't really want this file to last that long, so instead I'm doing a little bit of a trick, which I hope it's not gonna affect the accuracy of the emulation. And actually, everyone does that, so I don't know. So that's probably just that should be fine. At least at the moment, I can't see any issues with that. So if the address is, so the idea is within this read routine, so depending on the address range, we can return from the we can return the address from the different variables or from the different arrays, meanwhile adjusting the address so that it kind of maps properly to exactly where we want. So actually, if we want to get the value at, let's say we want to get a value at the absolute address of FFFC, right? So we say an address which is equal to FFFC minus FFFA minus the first element here, and then we get the adjusted index, the properly adjusted index. So we just so we actually would read here FFFC, we would read here, and FFFD would read here. And assuming the little endian byte order, we see that 1C22 is the address that is getting that the program counter is getting set to. So after this reset fires, the program counter starts being equal to 1C22, and this is already enough to get into it, just to have an idea what happens next. So next we need to find the address 1C22, and it's available in the ROM. So we go into 1C00, okay, 1C22, here it is. And quite a fun thing, so KIM entry reset RST. So let's say you've just turned on your KIM, and I'm not sure what happens if you just turn it on, whether it flashes the lights or not, but I know that you need to press the reset button. I saw this somewhere in the video. So once you press the reset button, the program counter gets the value of 1C22, this address, and he starts pointing to this byte. So this becomes the next instruction to execute, and then this one, and this is loading the value of FF to X register. So it's already the ROM code, so we don't need to know what exactly it does at the moment. We just need to make sure that the CPU actually starts executing bytes from here and down below there. So that's what we need to know. That's one of the most essential things. So, and it actually does. And from that point, we can already see like what's actually happening to the program counter. So, what's going on there? And this particular 6502 emulator that I'm using here has this nice log function, and well. Yeah, I didn't use this nice little log function. Yeah, instead, well, we can actually use that as well. So let's have a look what processor is going to be telling us after kind of running. So let's open the developer tools, and I just scroll up a little bit. So program counter 0, program counter 1C1F. Program counter 0, program counter 1C1F. So it jumps from 1C1F to 0 back and forth. Okay, I'm just wondering what's going wrong with it. Yeah, stack. Yeah, stack is also used along the way, which is interesting. I'm just wondering, stack should be FF at start. Yeah, and stack indeed is FF at start, which is exactly how it should be. So yeah, 1CFF, yeah, so it was executing some instructions, was doing something, and then once it got to this 1C1F 0, 1C1F, 1C1F 0, so we can now see what's going on there. So why is this happening? And I just want to close this, And yeah, hopefully if it's not laggy, then we can actually leave it as is. So 1C, 1C, okay, 1F, 1C, 1C, 1F, I forgot. Okay, so 1C, 1F, 1C, 1F. So now, it's sort of a detective story. So 1C, 1F, and we're going to 1C, 1C, 1F. Nope, 1C, 1F, here it is. And quite a fun thing, interrupt trap. And this really looks like what it does. It really looks like it's trapped because it kind of jumps back and forth. It is jumping back and forth if I just enable that developer tools. So, and here, even more interesting thing, which actually gives us an idea what to do next, right? So what we did so far, we just did set up, we just reset the CPU and provided the ROM, which provides the address of where the CPU is about to point its program counter to. That is stored at FFFC and then FFFD. So here he jumps to IRQV. We don't know what is that, but we see the address. So it's the address of 17FE, and this address is already, well, I believe this already should be in the 1K of RAM, not the ROM, but the RAM. And just to figure out if that is the case, actually, so I can go to the hexadecimal mode in the calculator, just trying to enter this address of 17FE, 17FE, and I want to convert to decimal. It's a little bit, well, I'm not exactly sure. Okay, so not, I don't know, I'm not sure where exactly, so RAM should be from 0000 and plus 1K. Okay, so, sorry, a bit of a stuck here. I just didn't test that yet. So another, yeah, another thing to consider. So here we have, it's where did this addresses kind of appear in. So here I have the first book, a book of KIM. And here is the caution here. So before running this or any other program, be sure that you have set the contents of the KIM vector locations as follows. So at the address 17FA should be 00, 17FB 1C. So yeah, because of the little linear order. And 17FE should be 00, 17FF should be 1C. And well, I guess this should be the address. And assuming that the jump, where was the jump? 6C. So 6C, I know that 4C is direct jump, so 6C should be the indirect jump, which tells us that this 1C00 is an address that it's going to be jumping indirectly to. Just to show you that, so if I go to the opcodes and go into the jump opcode, oh man, where is the jump? Jump is here. So we have this indirect address in 6C. So we know that here 6C jumps to, indirectly jumps to the address that is stored at 17FE. And we see that at 17FE, we're supposed to be saving the address of 1C00. And actually 1C00 is the entry point. Well, actually it's used, yeah, it's used for non-maskable interrupt. Yeah, so we kind of, so here we're supposed to be jumping from here, we're supposed to be jumping to 1C00, and actually we're gonna be trapped here. Yeah, trapped here. Okay, so the only thing that I'm slightly not clear about is so as far as, so if they say that it's possible to set this address, I'm just not sure whether it's in RAM or where the heck is that. So that's a bit of a question. So yeah, but actually I didn't get prepared for that, so I'm just starting with this sort of a thing. So I'm referencing when I don't know, just to have a sort of a clue where to go. I'm using the KIM-1 emulator of KIM-1, and here this read and write functions are known as read 6502 and write 6502. And if I just try to enter 1FEF, no, so again, what was the address? 17FE, I'm sorry, 17FE. Okay, so it's actually 17FE. So where is that supposed to be? This is what user is entering manually when powering on the KIM. Why not to do it here? Yes, exactly. So yeah, this happens in RAM. So yeah, I'm not sure yet what this is. RAM 002 is not the same as ROM 002. So this is probably, yeah, so at least when it's running on Arduino, it's probably located somewhere in the flash memory. So I'm just the kind of the next step. So in order to proceed consciously, what I need to figure out is what are these addresses a map for? So what are they basically? So is this really a RAM, or actually the KIM's RAM is going from 000 to plus 1K? So it starts at it should stop at just to give an idea what confuses me here. So going to hexadecimal. Well, no, let's go to decimal actually, and so we convert this to hex. Yeah, so 400s. So I just want to say that say here, so 0x00 to 0x0400. So this is the 1K of unexpanded KIM-1 RAM, and the address 17FE goes beyond this, and the fact that we can set that manually via the keyboard, it tells us that it's not in the RAM, and I just need to figure out where exactly that is. It's not a problem to implement that, but I just really want to figure out what is that. So well, actually this is all I can say up to this video, guys. So I know I can hardly believe this was useful to somebody, but I just wanted to give you an idea how this kind of detective story is going on, and how am I like looking for next steps, what I need to do by inspecting what actually how the processor operates, and what addresses in particular are getting fired, and why this addresses are firing from, like in the certain circumstances. So that's kind of the approach. So once this was the initial step. So the initial step was actually to make sure that the program counter loads properly and points to the RAM and starts doing something within the RAM. And then actually we're going further on. So once I get clear a little bit better of this address is 17FE and those nearby, hopefully I'll make another video explaining what exactly that means and where exactly in the real hardware it's located, because it really goes above the 1K of RAM, so it should be somewhere else. I have no idea where exactly, but yeah, it's really need to figure that out. So hope the Code Monkey Games approach is now clear. So we'll see how far will this bring me eventually. So this is it from my side, guys. Thanks for watching. Until the next time, and take care.